Well, good evening, and I want to thank you for joining us on another episode of the Fireplace Show. And the Fireplace Show is an outreach broadcast. It's sponsored by my company, CVC Success Group. My name's Jerry Eisenhower. I'm your host every week on this show. And again, what we want to do is share with you, the consumers of America, helpful information about your wood stoves, about your fireplaces, different questions that you may have. And tonight we got a couple questions we're going to deal with. The first one's going to be, what's the difference in a wood stove made today and one that was made 40 years ago? I mean, they're advertised as cleaner burning, longer to burn times, and all these other things. So what's the difference in these types of units? Well, that's going to be one question we're going to deal with tonight. Another question we're going to deal with tonight is, what is this cold air that's coming down my fireplace? Every time I sit on my hearth at night, or you get over there and we got cold air coming in when we're not using that fireplace. Some of these are even gas fireplaces, direct vent gas fireplaces that have glass over the front, but at the same time, it's cold right there in front of the fireplace. So we're going to try to answer that question tonight for you and show you how you test these things and how a technician will help you solve your problem. So stick around with us. We're going to be right back. We're going to play our intro music, and we'll be right back, and we'll get started with tonight's show. And I appreciate you joining us as always. So, like I said, hey, we're going to talk about some of the problems and some of the questions that come in from consumers and try to help get you a little bit of education about this tonight. Appreciate it, Lynn. Appreciate you joining me. And I really appreciate you sharing it out there. So we're going to be talking about wood stoves. And, you know, over the last 40 years, wood stoves have went through a tremendous change in technology and other things. So what we want to do is be able to share these things with you so you can grasp an understanding of what's out there in the real world and what makes today's wood stoves so much different than what we would have bought in our younger days, possibly what your parents or even your grandparents may have had. So what I've got right now on the screen is a picture of two different wood stoves. And I want you to kind of focus your eyes to the one on the left to start with. Because if we go back into the early 80s, into the 70s, what happened in the United States was we went through what was called the Arab oil embargo. And what happened was fuel costs rose dramatically, but also there was a scarcity of fuel. In that time frame, we went through a lot of changes. We had gas lines, we had laws considered, all kinds of regulations came in. So the end result of this was, after President Jimmy Carter went on television one night and he advised consumers of America, the citizens of America, that they needed to turn down their thermostats. He told them they needed to wear a sweater in their home. But what he also told them was they needed to start using their fireplaces to put supplemental heat into their home. And what did this do? It started to switch to alternative fuels. Even though wood stoves have been in existence for a number of years, they really weren't widely used until we went through this Arab oil embargo and energy prices that were rising dramatically. And I was living during this time, so I remember it very well, the gas lines we went through. And I actually had one of these older wood stoves that was installed in my home in the 80s. So on the left, what you're looking at is what we would consider to be an older wood stove, which is basically a box. It could be made out of steel, might be made out of cast iron, could even be made out of soapstone. So what did we do in here? We burnt the wood in the appliance, and then the heat was radiated off the appliance. Or we may even have a blower system where the blower would accelerate the heat coming off of that wood stove. But the problem with these older wood stoves were they weren't real efficient. They also created a tremendous amount of smoke and started endangering the environment. So wood stove manufacturers started making advances. And if you look to the unit to the right, you can see I've got a red arrow on that stove pointing at a diagonal line. And that's what's called a baffle. And wood stove manufacturers started putting baffles in their units. Now, what did the baffle do? The baffle created turbulence inside of that wood stove, which increased the efficiency of the wood stove tremendously and got more heat out of it, but also removed a lot of that smoke that was going up the chimney. But around 1985, 1986, somewhere in the mid 1980s, we had a division of the federal government, the United States government, called the Environmental Protection Association and Agency. And what did they do? They started regulating the way wood stoves could be built, and the matter of reduction of the smoke had to start occurring. So around the mid 1980s, we started having new style stoves that came out that had new styles of burning systems in them. So we're going to go to one here. And the first that came out, and one that was used for a number of years, is what we call a catalytic wood stove. And what did they put in a catalytic wood stove? They put a catalyst, which is an element that all the smoke and the gases passed through this catalyst before it got to the chimney. So what we're doing is we're running the smoke through the catalyst. The catalyst is taking all the ingredients of the smoke. It's taking the hydrogen that's in the smoke. It's taking carbon monoxide, methane, acetic acids, and the hydrocarbons, and runs it through that afterburner system, what we call the catalyst, just like what's on your car. So out the other side, what came out was water vapor and carbon dioxide. So how did this happen? What did this system do? Well, it actually changed the chemical composition of the smoke and the gases. Normally, it would take between 1,000 degrees Fahrenheit and 1,600 degrees Fahrenheit in order to burn up these pollutants before they went up the chimney. But with the catalyst, we were able to lower this to where we could burn this at the 500 to 700 degree area or range of temperatures. So by doing this, we were able to lower the amount of smoke that was going out of the chimney. And by doing this, we were able to meet the EPA clean burn standards that were being put into effect at this time. So the catalytic wood stove, that was where we started to reduce the emissions in the atmosphere, but also increase the efficiency of the wood burning appliances. Now, even as we went through this, there were still changes out there that the wood stoves went through in their evolution to become clean burning. So the next type of stove that came out was called a high-tech wood stove. And what did a high-tech wood stove do? The high-tech wood stove allowed the combustion products as they were going through the top of the appliance to meet fresh air that was pulled in through afterburner bars. You can see on the photo, you see with the number 3 there. Well, that's the afterburner bars. So what's happening is we got fresh air coming into the appliance. It is preheated, and then it mixes with the smoke and the gases right in the top of the appliance. Then you can see by the red arrow how the smoke and the gases went around and went through a secondary burn chamber in the top of the unit. So this was another way of cleaning up the wood stoves and reducing the emissions, but also giving them much more heat output into the room. The stoves were more efficient. They got a cleaner glass. We were just getting better and better with the output and what these new appliances could do. But we weren't then there because EPA continued to make requirements for reduced emissions. They were on this mission. So in this period of time since the mid 1980s until today, EPA has continued to regulate the wood stove industry to where the smoke that comes out has to get less and less. Now, I've showed you the catalytic unit. I've showed you the high-tech unit. Now what you're looking at is what we call a hybrid stove. And what is a hybrid stove? A hybrid uses a combination of the high-tech design and also a catalyst into it to make the stove produce much less smoke, much less gases, and produce much more heat into the room. And this is why the newer wood stoves of the day are going to be much more efficient. They're going to burn much less fuel. They're going to give you more heat per pound of wood. Now, one of the questions that always comes up, what about the pollution from a wood stove? Well, here's the true facts. If you let the trees rot when they fall in the forest, it produces more harmful effects on the environment than clean burning of wood. When you look at this, this is an extremely clean burning design. And the goal through all this is to reduce the smoke, the pollutants that go into the atmosphere. So this kind of photo shows you here, if we go back 20 years ago or to an open fireplace, you can see that we are producing a lot of pollutants that go into that atmosphere. As we built and changed the stoves and the designs, the amount of smoke was drastically reduced. And now we have what's called an eco-design ready stove. And the newer stoves that are made today produce very little pollutants into the atmosphere. They're very clean burning. They're not harmful to the environment. So this is kind of the advances that have gone on. Now, do today's stoves cost a whole lot more than the stoves did in the early 80s? Well, you better bet it does. And why? Because raw material prices have gone up tremendously, and we also have a rising cost of labor. So when you look at a stove today, is it going to be a lot more expensive than that unit was 40 years ago? Yeah, I'm afraid it is, because that's the one thing we can control is the raw material costs that are utilized in there and the labor cost of products, which continues to rise. So this has been just some general information for you about why today's wood stoves are such great appliances and why they are much less polluting and why they're actually good for the environment. So that should give you some thought processes. If you have any questions, you can see my email address on the screen. Feel free to send me an email. That's what we look for here, because what we love to do is answer questions from consumers on this show that are submitted to us every week. And that's where we come up with the information we're going to present and the subject matters that we go over. Now, there's another problem that we want to talk about, and this is the matter of cold air coming down the chimney. You see, this is a big problem a lot of times where somebody will have a fireplace and they'll want to put glass doors on it. But around that fireplace, we've just got cold air coming down that chimney. But there's also other areas of the home that cold air are pulled into, and we'll commonly call these drafts. So here's the question. Why is this happening? Why does the cold air come down the chimney as it does? And there's a really simple reason for this. And the reason is it's something in the industry that we call negative pressure, because the pressure downstairs where the fireplace is actually lower than the pressure at the top of the chimney. And when this happens, the cold air is pulled down the chimney. Now, you may think, hey, I've got a damper to my fireplace and I can close it and that will stop this. But the problem is that damper is not airtight. So air can still be pulled down the chimney around where that damper is, even though it's closed, and that cold air can come into your home. It can also be pulled through cracks, small openings in the chimney, defects in the chimney. But what's causing it is the negative pressure in the home, where the pressure is lower inside than it is outside. And what this does is creates a vacuum in the home. And under this situation, any areas that are under negative pressure will pull air into the home. Now, we also have to factor out positive pressure. And positive pressure, if we have positive pressure in the home, then the air is going to be pushed back out of the house. But see, this is the thing. In most homes, on the lower level of the home, due to the science that's involved here, if there's any gaps, any holes, anything there, then the air is going to be pulled into the home. And if it's cold like it is right now, when this air comes in, it's going to be very cold air. And these are the drafts that we feel. You may sit in a chair and feel a draft come across your feet and across your legs. But this is from the negative pressure that's pulling the air from outside into the house. And this is what we would call a non-conditioned air. In other words, it doesn't go through your heating system. It comes in to where it damages the comfort in your home. Now, if you're feeling this, if you're going through this phenomenon, if this is happening, your question is, what do I do about it? Well, the first thing is you got to understand the problem if you don't understand it. And we have something going on here that's called stack effect. And stack effect is where when the air enters the home, it is heated. And the heated air, due to what's called natural convection, is going to rise. And it's going to rise up. And if there's any openings on the upper level of the home, this air is going to be sucked out of the house. Remember, it's on positive pressure up there. And you can see on this slide on the right-hand side, you see where it says the neutral pressure plane. Well, the neutral pressure plane is where the pressure is equal. Below the neutral pressure plane, we're going to be in a negative situation. Above the pressure plane, neutral pressure plane, we're going to be in a positive pressure situation. So below that neutral pressure plane, we're going to pull outside air in. Above that neutral pressure plane, what are we going to do? We're going to push heated air out of the home. And this is where a lot of people are losing a lot of their heat, and their utility bills are rising dramatically, because what you're doing is you're heating air for your home, and then it escapes from your home, and you're pulling cold air from outside into your house that replaces that air. And in colder climates, this can be rather severe. Might be why your feet are cold at night. Might be why, hey, it's just not so comfortable. And it might just be why your utility bill, your gas bill, your electric bill, it might just be why these are climbing. So stack effect, what's that's caused by? That's caused by the natural currents of air being heated and rising and escaping out the upper level leaks, which in turn creates a suction at the lower level and pulls the air into the home. So these are the things to be aware of. Now, also, there's another consideration in this. And the other consideration that can cause the negative pressure, which we also call depressurization, is going to be all the mechanical systems located in your house. The mechanical systems are going to be things like your kitchen range hood that you turn on when you cook. It exhausts air out of the house. You've also got a clothes dryer, more than likely. Whenever you turn that clothes dryer on, it's going to exhaust a lot of air out of the home. If you go into your family's restrooms, your bathrooms, usually there's going to be a fan up there, and the fan is going to exhaust air out when it's turned on. So we have an issue here with both stack effect and also the mechanical venting systems in the home, because together these are exhausting a tremendous amount of air out of the house. And it's a very, very real problem in much new construction today. And this is what we call the negative air pressure problem. And it exists in many homes. And with today's world where we see green construction methods, we're seeing that this is an increasing problem. In fact, it makes many fireplaces hard to operate because we simply don't have enough air coming into the home. And how to solve this. So, what you've got to do is be able to test for this issue. So I've got a couple things I want to show you, and these are some of the tools that a technician would use in order to diagnose the issue. And the first is, this is an infrared or IR thermometer. And with an infrared thermometer, what does it do? I've actually got a light that comes out of this. It's a laser light, And wherever it points at a wall, it's going to measure the temperature where it hits. Like right now, I'm shooting it at a wall, and that wall is 72.6 degrees Fahrenheit. If I shoot it at the ceiling in the room that I'm in, the ceiling is 78 degrees Fahrenheit. Why is it warmer up there? Because of the rising air currents. If you measure the temperature, you're always going to find it's going to be warmer at the higher levels than it is going to be on the lower levels. This is natural convection. This is a natural phenomenon, and it happens in any type of construction. Now, one of the things that a technician also uses is a device that we call a manometer. Now, what does a manometer do? A manometer actually measures air pressure, and we measure it in a unit of measurement that's called a Pascal. The unit of measurement of pascals was invented by a Frenchman many, many years ago by the name of Blaise Pascal. And to give you an example of pascals, if you took an ordinary bicycle tire and you measured the pascals in that bicycle tire, it's going to hold about 400,000 pascals of pressure. Now, pascals are used to measure other things. It's a very, very finite measurement when you've got a Pascal. Okay, so but we're measuring in that, and here we're using a manometer, and a manometer is a device that is made to measure pressure, and we measure it in pascals. We can also measure it in psi, which is pounds per square inch. We can also measure it in water column, and water column is what we use to measure draft in a chimney. But it's a very, very useful tool for a technician to have. So these are two of the tools. Another tool that we utilize is an infrared or IR camera. Now, what does the IR camera do? The IR camera takes a picture and the color changes with the temperature change. With an infrared camera, we can detect the temperature change up to 1/10 of a degree. That's right, 1/10 of a degree. So the infrared camera, what we do for that is we take a picture of the walls. You can take pictures of anything. You will see the temperature variations. Now, as you start going through this, it's really amazing when you start seeing, like at your molding where your ceiling meets your walls, your electrical outlets. It's really amazing when you see the temperature variations, and what it's caused by is caused by the air that's either being pulled into the home or being exhausted from the home. So the infrared camera is also a way that we can go through this. Now, this is where you're really getting down to do the test. And this is called a blower door test. And with the blower door test, what we're doing here is we are putting the home under a minus 50 Pascal pressure by a fan in the door. And you can see that he also has a manometer mounted there, and he has a computer also. So this is kind of an involved technology process where you're going to test the home to help you locate where these leaks in the system are. And they locate them by use of the infrared camera. They note them by the pressure, which the manometer is reading. The blower door mounted in the door is going to exhaust the pressure out. Now, in order for you to understand this, what I'm going to do here is we're going to actually, if I can get my slides to cooperate here, I'm going to show you a video tonight of a blower door test that is underway so you can understand what blower door testing actually is. So this will be pretty interesting. This is going to run about 9.5 minutes, but I'm going to show you in this what a blower door test does.
For door test, we follow the BPI, the Building Performance Institute, the national standards or protocols, such as testing for any gas leaks in the house using gas sniffer. We also put the house in its worst case conditions, which is for the CAS zone, which is typically where the water heater and or furnace is located. Any of the natural venting appliances, like an 80% furnace or an 80% water heater. So we want to see if all the fans in the house run, like the bathroom fans and the stove fan. if it's going to make it so that that appliance can properly vent, can it properly exhaust. If it's going to backtrack, and if it's going to come into the house, or if it's going to spill, we call that spillage, then we have a way of testing for that, even before the blower door. So one, we know that the house is safe, and two, we know that the equipment is still going to operate effectively, even in its worst case conditions. So once that's done, once we go through the safety protocols and we set the house up in what we call wintertime conditions, all the doors and windows closed, make sure the fireplace is properly, the ash is cleaned up and covered, or any drains possibly in a basement or in a crawl space. We want to pour water down those traps. We want to make sure we're not bringing anything harmful into the house environment, because the blower door pulling the
Volume up.
and from all the nooks and crannies in the house, we're going to measure what that is. That's going to give us our air number, or what we call our air changes per hour. And we know that. We want to let the homeowner know where's their house at with a baseline. So once we do the first blower door, that puts the house in, that gives us a baseline number, so that as we do improvements, whether it's attic insulation or crawl space or spray foam and rim joists, sealing up doors and windows, we'll be able to measure the house after all that work is done, so that we know what it was before, and through proper diagnostics like a blower door, we'll know what it is after. Now we're installing the blower door, so you get a good tight seal. First the frame was set, then the cloth was put onto the door frame, the blower door frame. Now I'm just setting it back in the pocket, and you usually don't take the Velcro off, but these are the clamps that, once I set them up, they're already tightened. This begins to press the door into shape. So I'm going to do that at each of the points. There's one on top, two on the sides, and one at the bottom. And now, of course, we have a big hole, and we're going to fill that with the fan. But before I put the fan in, I have to run what's called a reference tube to the outside so I can measure outside air pressure. So this frame also helps to tighten the midsection of the door. And it also supports the fan when I put the fan in. So with a blower door manometer, we need to be able to measure the outside air pressure with reference to the inside air pressure. So that's what this red tube is for. This is going to go through the blower door. There's a small hole on either side. I don't know if you can see it. And that just runs to the outside. And then we try to get it as far away from the actual blower motor itself so that the air that's being pulled out of the home doesn't affect the manometer's reference to the outside. So I'm going to be also putting in some of the tubes into, and I'll be showing you that in a second. But this is the support bar that's going to hold the fan, and a simple Velcro strap allows me to lift the fan just a bit, put it in a nice tight fashion, make sure it's got a permanent tight seal all the way around it, and that completes just the blower door installation. Now I'm going to hook up the correct harnesses to both the control and to the Retrotech DM32 digital manometer. So there's actually 3 rings. This is the first ring. This is the second ring. And this is the third ring. So you might say, how do you usually run the blower door? If it's a really big house, and I know it's an old house and it's really leaky, I may start here. Typically, I will start with the B ring on a smaller home, because the nice thing about these manometers, it can actually show me the efficiency of the fan speed if it's running at 60, 70, 80, 90, or 100% of the fan speed, which I don't want to run it at 100% because I don't know if it can go any higher. So I like to run it between 60 to 70%. This is the next ring. I'm going to put this back on. And the great thing about Retrotech is right on the manometer, or even on the remote, I can just click on and it shows me a picture. Is it the B ring, the A ring, or the open ring? Well, with all 3 off, it's open. With 1 ring on, it's A. With 2 rings on, it's B. So I'm going to select B. So it's set up. I have a baseline. I have the B ring open. I've done the safety protocols according to BPI standards. We tested the house if there were any gas leaks. And the next was we did the water heater. We Set up the CAS zone, the worst case conditions in the house, through bathroom fans, through kitchen exhaust fans. And we wanted to see if the water heater would pass once we fire it, take it from pilot to fire, to see if it'll exhaust on its own or will it backdraft into the house. The water heater passed. So now I'm ready to actually run the blower door. I set the house up in wintertime conditions, which means all the doors and windows in the house are completely closed, as if it's wintertime, and I'm going to turn the furnace on heat because we don't want any windows open, because that would affect us measuring the amount of leakage in the house, whether it's through windows or can lights or maybe an attic access in the attic or in a closet in one of the bedrooms. You know, there's going to be air leaking in through all areas of the house, the rim joists or areas in the basement. So we're going to be able to calculate all of that air leakage at one time with the blower door. That's going to help us to better analyze and diagnose what's going on structurally in the home, so we can better analyze and understand the load calculation, the manual J, and how to best size equipment for this house, and or any other home improvements such as attic insulation, spray foam, air sealing in the attic, windows, doors, things like that. And I can either set the pressure or set the speed. Setting the pressure allows me to set, I want to get my final number at Pascal 50. I would run it at 25 Pascal if I knew that there was a wood-burning fireplace in the house or something that had ash. If there was a fireplace, we would, of course, clean out all the ash in the fireplace, close the flue. I would run it at 25 Pascal so I can go and do a safety check so that there's no black soot or white soot or anything coming into the house. At 25 Pascal, it's about half speed. So that's, again, another safety protocol, that we just don't fire up the blower door and run it, because what if I'm going to cause damage or harm to that person's home? So I'll set it at 25 Pascal just as an illustration, 25, and I hit set. Set pressure, 25 Pascal, go. Now at 25 Pascal, I can literally just push a button to increase it at 5 Pascal per button push, and I can ramp it all the way up to 50 Pascal. As the fan increases in speed, I can monitor and watch. So now that the blower door is running at 50 Pascal, I have 1,668 CFM at 50 Pascal. So that lets me know what my air leakage is. So the great thing about the remote and the DM32 digital manometer is I can go right into it and switch the screen over to air changes per hour. So I can do the log math on that, or I can let the actual device itself tell me exactly what that is. So right here it says air changes per hour. I can select that button. I can go back to the main menu. And this house is actually very tight. It's 3.05 air changes per hour. And for new construction, they're looking to get 4 to 5 air changes per hour in the new home for the 2015 IECC National Energy Code. So this house is actually really tight. We might talk about an ERV or HRV so that they can bring in more fresh air. A lot of houses that haven't had work done on them may say anywhere from 8 to 12 or even as high as 20 air changes per hour. So the higher the number, the higher the blood pressure. So this is a really great illustration on how many air changes per hour is possible in a house.
Okay, so let me get my video off here. Sorry about that. But anyway, let me come back here, stop sharing. And I'm back on your full screen now. So anyway, I wanted to show you that because that was called a blower door test. So what you've got to do to be able to resolve this issue of why is the cold air coming down my chimney? Why am I having drafts in my house? And the problem with this is, like I said, it can be a very high energy cost can result from this. You've got to test the house. And I showed you the blower door test, that's the most advanced way to test it. Like I said, there's some devices we use. I showed you the manometer. He also used the manometer in the blower door test. I shared with you the infrared camera. I shared with you the laser thermometer. But these are all various testing tools to try to locate this issue. So again, This has been this week's episode of the Fireplace Show. We wanted to share with you what some of the differences are with older wood stoves and the wood stoves that are sold today, and wanted to help give you some information of why the cold air is coming down your chimney where it may not be very comfortable right in front of your fireplace, but it could be other places in your home where you've got air leaks. So I appreciate you joining us tonight. This is the Fireplace Show. This is sponsored by CVC Success Group, and my name is Jerry Eisenhower. You see my email address on the screen right now. If you got a question about your fireplace, you got a question about your gas logs, you got a question about your chimney, you got a question about any type of hearth appliance, then send us the question. We'd love to make it the subject of a future episode of the Fireplace Show. And with that, hope you have a great evening. And again, thanks for joining us. It's truly an honor and it's a pleasure to be able to share information like this with you on each and every episode of the Fireplace Show. Talk to you later. See you on a future episode of our broadcast.